What's up, everybody? It's Miss Wesley, and it's calc time. We are on u-Substitution. I've almost lost track of the day. I think it's day 5 of u-Substitution already. And we're looking at your u-Sub packet. The problems I'm on, I don't want you to get too scared by this heading, because it's good that we're looking at this together. It says complicated, right? But maybe we can make the complicated a little bit less complicated if we work together. And it's on, what page is this? Page 8 of the packet. There is a little turtle peeking at you from the top. You guys have caught me while I've cracked open a nice mini Dr. Pepper, so I'm ready to go. I'm ready to take some integrals here. And I have a question for you before we start. Why does P. Diddy have such good hair? Because Sean Combs. That's his name, Sean Combs. Number 1. Look at this crazy problem. Okay, so it says you want to integrate, take an indefinite integral of x squared times secant of x to the third, tangent of x to the third. And we want to make a u choice first. So I'll give myself a little room over to the side to figure out what u is going to be. And we'll try 3 or 4 of these, and I guarantee you the toughest part usually with these is going to be making the right choice for u. And we have a couple options here. We've got the x squared, we've got the secant part, the tangent part, and don't sleep on the x to the third part. I'm leaning a little bit toward that. Usually we look for a more innermost part of the function, and I feel like there's a strong case that could be made for setting u equal to x cubed. Let's think of the benefits of setting up this substitution. Number 1, no, it's not more complicated than the trig, but it is more complicated than x squared. It's a higher power. Number 2, it's definitely more inner than x squared is because it's within a secant and within a tangent. Number 3, although its derivative doesn't appear, its derivative is to the second power, so the power of its derivative appears. I bet you it'd be a good way to get rid of x squared, and I'm not that scared of being left with a secant tangent because I feel like I recognize that one from my list of trig antiderivatives. So we're going to go with this substitution and work together to see if we can solve. Okay, so side work, du dx, take a derivative. 3x squared, looks okay. What was the next step? We had to work to solve this for dx. So du equals 3x squared dx, and du over 3x squared equals dx. One of your classmates told me, and I say this all the time, it's kind of like you're solving a puzzle. U-Substitution is like a little integral puzzle where you've got the puzzle pieces, you have to put them in the right spots to make this an easier to handle integral. So here goes nothing. Integral of x squared. How can we write this part? Well, we call these things u, right? So I'll write secant of u, tangent of u. With a dx, for which we can plug in what I circled down here. So du over, oh, excellent, 3x squared, one little victory is the x squareds going away. So x squared up top cancels with an x squared on the bottom, and the 3 is okay to stay. We're going to integrate 1/3 secant of u, tangent of u. And this one just got a lot less scary. This is on our list of trig antiderivatives. Like I said, think of a function who has this as its derivative, and that function is going to be secant. The 1/3 stays because it's a constant. The integral of this expression we can find as secant of u with a plus c. And then last but not least, we plug back in. Man, this one looked, I think, a lot worse than it became. Once we picked the right u, secant of x cubed, we'll leave it, it made it a lot quicker to integrate. Now, I know what I would be thinking at this point. It's all well and good when we talk it through together, but how am I going to know to choose x cubed to be my u? I think you'll see some of the hints about innermost and a higher power than the x squared is. And honestly, if we made the wrong u choice, like if I tried x squared, I would do the side work and notice that not enough stuff would cancel. So the comforting thing is trial and error works. I've got an eraser. Even on this crazy program, I can figure out how to delete things if it doesn't look good. And then we can have no problem solving. All right, if you don't mind, number 2, I'll move to the left side of the paper, but number 2 is uncharted territory. We've seen integrals that have trig in them. We've seen integrals that have natural logs in them, but I don't think we've seen an integral yet with the sign of a natural log. So here goes nothing. Let's do the side work. Let u equal. This is the part I want to be really thoughtful about, because if we set ourselves up with a good u choice, the rest of the problem should be pretty painless. And I think we've got options. It's either the sine of the ln of x, or maybe it's the inside, the ln of x, Or maybe it's just x. I can't think of any other choices besides those three things. I feel like part of this has to be off the table. Like x never really does much. If we just said x was equal to u, we wouldn't have a simpler expression here. I don't think that'll ever happen. So which one do you pick? It's hard to compare a trig function to a transcendental natural log function, right? So you can't say one is more complicated. I guess this would be a little more complex than that. So go with the innermost. What's more inside, the sine or the ln? Let's use ln. I wonder if looking at the problem, you notice like an added bonus of using ln as your u choice if you see its derivative appearing. So speaking of its derivative, that's what we're about to have to find, du dx. Well, we've got to think back to the old days. Derivative of ln, we saw this yesterday, is 1 over x. That is awesome because that appears in the original function. I don't know how excited you are, but I'm pretty excited about this. It's going to make something cancel. So let's cross multiply, and you get the joke that I made yesterday too, the x du concert. Equals dx, and this is now solved. So this times that, dx times 1 equals x times du, and both of these are our puzzle pieces. I think we set ourselves up nicely. I don't think this one's going to be that bad anymore. Let's go back to the original and see what we can plug in. So integral of the sine of, can we call that u? Yeah, we said u is equal to ln of x, so the sine of u over x, but that x isn't going to stay for long. We plug in x du. For dx, I get to cancel the x on top with the x on bottom, and there's not much else getting in my way. A crazy looking integral, we've just made it look a lot simpler. You're just integrating this guy in terms of u. So think of sine's interval, right? Think of a function that has plain old sine as its derivative, and that's going to be negative cosine of u plus c. Love it. And now we'll plug u back in. So we'll plug in for x in terms of u, right? Cosine of, we called u the ln of x plus c. Again, if we wanted to, we could take a chain rule and derive this, take a derivative of this, and see if we get the original back. And we really should. That should be a good answer. Okay, so we're making our way down the page, and these just get tougher and tougher as you go down. I like the looks of number 3. I would love to try this one with you with a binomial up top and a trinomial in the bottom. I said I'm liking the look of this because I really do feel like we have that classic 50-50 choice for what u should be here. It's either going to be the top expression or the bottom expression. Here's one where I see a fraction, so I do need some sort of substitution, but I don't see like a power on the outside or a square root like you see in number 5 where you just have to pull off the inside. So really it's a 50-50 choice. Are you picking the top or are you picking the bottom for you? Pick the one that looks a little bit more complicated, right? Pick the bottom because it's to a higher power. And its derivative maybe sort of semi-appears, but at least I know the power of its derivative also appears, so we might get lucky and get something to cancel. So du dx, let's do some side work, differentiating. Take a derivative, 2x plus 4. Kind of related to 3x plus 6. It's not exactly the same thing, but they are associated with one another. Let's see how. So du equals 2x plus 4 dx. And du over that binomial, if you want to take it that far, equals dx. So this can be plugged in for dx, and this can be plugged in for u. Let's go back to the original. And let's go crazy and switch to purple, which is my favorite color. So integral of 3x plus 6 on the bottom, u, right? Dx, I can plug in this fraction. So du over 2x plus 4. And then dum, dum, dum. This is the first time this has ever happened. Usually we're in such a happy stage here where I just get so excited about slashing things out and crossing things off. And here you can't. I just can't cross off this x with that x when I've got those other added things involved. Never fear. You've got to just notice a similarity between these two binomials. I was hinting at it earlier. Aren't they kind of multiples of one another? Couldn't we factor the top and factor the bottom, like a little quick GCF, and see if maybe, possibly, just maybe, we could get the x's to cancel? And the answer is yes, we can do it. Okay, so 3 comes out of the top, x plus 2. I like how that looks. How about here? There's a du up top. On the bottom, ooh, this is great, 2, and then x plus 2. That's what I wanted to happen. Let's get some green, and we will cancel the x plus 2's. Reduce that, and now all I'm left over with is an easy u expression and a couple constants. So we're integrating 3/2 times 1 over u du, like that. So this is 3/2. The 3/2 stays when you integrate. 1 over u is the only power of u to the -1 is the only power where we can't really use the normal integration rule, because going up a power, you'd be going up to 0, right? We can't divide by 0. Think of a function that has this as its derivative, and that would be ln. Remember the rule, ln of the absolute value of u plus c. Finishing touch, plug back in for x. So this is x squared plus 4x minus 3. And these have to be some of the toughest integrals we've ever taken together. Lastly, should we look at one that has a square root in it? 5 probably looks okay. Let's let u equal something. And off to the side, go back to blue. Off to the side, we will pick. We never make ux. I think that's a terrible choice. On the bottom, this could get tricky. Do we include the square root? Do we not? When you're just dealing with a squared down here inside of a square root and an x up top, pick the inside of that square root. Just pick the 1 minus 4x squared part. It's a little more complicated. It's innermost. That's key. It's inside of a square root, and the power of its derivative appears. Its derivative, as we'll see in a second, is going to be linear. So you just get -8x. This should be great. So du equals -8x dx. If you want to pause the video now and try to do the plug-in on your own, try to fit in the pieces of the puzzle, and then kind of join back up with me, turn it back on, we can see if we both subbed in the same way and if we both get the same answer. So feel free to pause and rejoin. I'm going to try to sub back in for number 5. You have an x up top, you have square root of u on the bottom. In for dx, we can plug in du over -8x. And that does the trick, right? The x's should cancel. Get some red in there. And we have, let's rewrite this. Let's go constant first with a -8 on the bottom. So -1 over 8. Next up is the square root of u on the bottom of a fraction. So let's swing that up to the top. We'll swing the variable to the top and write it to the -1/2 power. Good practice with fractions here. And here's what we have to integrate with respect to u. -1/8 is going to stay. We got to come up with 1 power higher than -1/2, so +1/2. And that works nicely as long as we divide by 1/2. So we multiply by 2. So we'll put a 2 here, plus c there. And we'll sub back in, so we have this in terms of x. Now, we can just call this -1/8 times 2. We can call it -1/4. How about those two coefficients multiplied? And in for u, we can plug in 1 minus 4x squared. I apologize for that handwriting. And that is all to the 1/2. I don't think I forgot anything. That should do it for that page. Those were some good examples. All right, could you do me a favor? Your homework's going to come from the page before this. These are good ones to practice. So I'm just scrolling back up if you want to turn over to page 7. A little bit of advice for a couple of these for starters. I want to start 6 with you. For 6, do yourself a favor. There was a rule in pre-calculus that said that if you have the log of something to a power, you're allowed to swing that log down to the front of the expression. So that's exactly what we're going to do here. We're going to make this, I'm going to rewrite this off the bat and use a pre-calc rule that says I'm allowed to write this as 2 ln x over x. I don't think I need to take you much further than that, because I think you're going to know what to choose for u if you look at the second question that we did on the next page. Choose let u equal ln of x. It's a great choice because it is a little more complicated. It's not really more innermost, but its derivative is going to appear. I think that'll take you far with number 6. When you get to questions like 7 or number 10, I have a suggestion for you. 7 and 10 are going to be really nice if you choose u to be the most inner part of this function. So it's either the x or the e part, or what about just the power? Try that. Try letting u for 7 and for the last question on the page just equal the power that x is raised to, the x squared power. It'll work nicely. Its derivative should cancel pretty nicely with the x that's out front. And I think you'll be fine with that one too. Please continue to ask questions, continue to have a good day, and keep up the good work. Drink Dr. Pepper or drink something healthier than Dr. Pepper. See you later.